Okay, so I guess you just watched the video on directed graphs. I'd like to now show you the Sage component to this lecture, which is kind of fun, I think. Uh, so the big idea here is that Sage, again, it's not just for linear algebra stuff. It does all sorts of mathematical things, and it turns out that Sage can handle digraphs. So here on the site, I've included a figure that I made. So here we have a directed graph. This one has 3 nodes, and it looks like 5 arrows. And in the first little calculator here, I've input what a person would need to input in order to tell Sage about this directed graph. So here's the syntax that works. So the first line of this code initializes a variable g and tells Sage that this is a directed graph. By default, Sage does not allow for arrows that are the same. So it wouldn't allow for 2 arrows to start and point at the same, or start at the same node and end at the same node. But it does allow for that functionality. You just have to turn it on. So I'm doing that in the second line of code here. The next thing I'm doing is I'm telling Sage that in my directed graph, I want 3 vertices called v1, v2, and v3. So here the vertices are v1, v2, v3. We called those nodes in the lecture. It's the same thing. And then the fourth line here defines all the arrows in the directed graph. Sage refers to these as edges. Edges means the same thing as arrow. And what this is we're constructing a list where each tuple in this list is a source node and a target node for an arrow. So in this directed graph, the first arrow points from v1 to v2. So in the first tuple in our list, we're writing down v1, v2. For the second arrow in this directed graph, the second arrow starts and ends at the same spot, so we're writing v1, comma v2 again. The third arrow starts at v1 and points at v3. So we write, let's see here, 1, 2, 3. Well, I guess actually I did that later in the digraph, v1, v3. That's okay. For the fourth arrow, we're starting at v2 and ending at v3, so I included that one here. And then for our last arrow, we started at v3 and point at v2. So that ends up that I input that one right here. So I didn't put them down in the order that they're in the figure, but that won't be a problem for us because, well, let me show you. So so now what's cool is the last line I write show g, and this gives us an automatic artistic rendering of the directed graph. So I have what I did in my spare time, I put this down, or I wrote code that generated this image. Sage automatically takes the data that we input here and generates its own image. So even though these don't look identical, they actually are. So if you look at v1 here, v1 has 3 arrows attached to it. 2 are pointing at v2 and 1 is pointing at v3. That's exactly what's happening here. v1 points at v2 twice and v1 points at v3 once. Cool. So that's how you initialize the directed graph. If you want the incidence matrix, you can use the syntax g.incidence matrix, open close parentheses. So again, for each one of these cells, I have to reconstruct the directed graph. So I construct the graph here, and then on the 5th line of code, I write a equals g.incidence matrix. And down here, I have a print statement, which will give us the incidence matrix. So here, the incidence matrix is 3 by 5, because this directed graph has 3 nodes and 5 arrows. And I believe the labeling that I put on the directed graph is the same, or is compatible with the labeling on the directed graph here. So the first and second arrow point from v1 to v2. The third arrow points from v1 to v3. The fourth points from v2 to v3, and the fifth points from v3 to v2. Great. Now, remember, another part of the lecture was about weighted digraphs. So for weighted digraphs, you add weights to the arrows, or you tag each arrow with a weight. So here I have the same exact directed graph, but now I've attached weights to each arrow. So I have these terrible numbers. A1 has weight 331, A2 is weight -470, so on and so forth. Now, remember, the big takeaway from this lecture on digraphs is you can organize the data of the directed graph in the incidence matrix, and then separately you can organize the data of the weights in what's called a weight vector. You can take a vector and just input all of the weights into that vector. And when you multiply the incidence matrix by the weight vector, you produce a new vector, and that new vector gives you the net flow through each node. So in this last calculator cell here, I have the code from before where we define the directed graph and then get its incidence matrix. And then we multiply by, or then we define the weight vector. So here, the weight vector is 331, negative 470, negative 674, 101, 17. So those are the weights that I've used in this figure. And this print statement here will tell us what A times W is. So if I click evaluate, it tells me that A times W is 813, negative 223, negative 590. Note, there are 3 coordinates in this output, and that makes sense because there are 3 nodes in the directed graph. So what this is telling us is that the net flow through the first node is equal to 813. I'm not even going to bother to do that arithmetic myself because I'm dealing with 3-digit numbers. I'm not even good at that. But remember that the mechanics behind that were to add weights pointing in and subtract weights pointing out. So here, there's nothing pointing in. There's only stuff pointing out. So we subtract 331 and then minus negative 470, so that becomes a positive. And then minus negative 674, that becomes a positive. And when you do the arithmetic there, you get 813. If we did it for V2, V2 is more complex here. We have 3 arrows pointing at V2 and 1 pointing away. So if we calculated the net flow ourselves, we would add the weights pointing in. So that's 331 plus negative 470 plus 17. And then we would subtract off the weight pointing away. So we would subtract off 101. And evidently that would give us negative 223. And finally, for the third node here, we would add 101 and negative 674. So that would give us some negative number. And then we subtract off 17, so that number becomes a little bit more negative, and we end up with negative 590. So the cool thing about this setup is I don't have to do any of that arithmetic myself. I can keep track of the data of the digraph in the incidence matrix, and then I can keep track the data of the nodes in a separate vector. The digraph, or the incidence matrix has 3 rows and 5 columns. The weight vector has 5 entries. But when I multiply the incidence matrix by the weight vector, we get a vector with 3 entries, and those 3 entries tell us the net flows through each of the 3 nodes. So it's a really cool application. I mean, this is really one of my favorite applications of linear algebra. We're going to return to directed graphs and incidence matrices a little further on down the line in this course after we've done a few other things. But I just thought this was such a cool application. I couldn't help myself. I had to include it. So hope you enjoyed it. That actually concludes everything I want to say about directed graphs for the moment. So.